Good morning. I can get this thing started here and not hit the wrong buttons. We're going to be talking about an introduction to, I think, the most difficult challenge in creationism. And they originally were going to have me talk for an hour, and then it was really going to be 50 minutes, and now it's 45, and now we're a few minutes behind. So I don't promise to get all the way through. But we'll get as far as we can, and then we'll try to maybe answer a few more questions in the question and answer period when it comes. A little overview to what we'll be talking about. We're going to start out with varieties of radiometric dating. We'll just go through that. And then we're going to talk about the general principles of radiometric dating that apply to all forms of radiometric dating. Then we're going to talk about potassium-argon dating and argon dating, which is part of the same method. We're going to talk about uranium-lead dating and zircons. We're going to give you some stuff on isochron dating, including rubidium-strontium dating, but there's a lot of other varieties. And we're going to talk about uranium disequilibrium dating very, very briefly, because we really don't have time, and it's complicated. And then we're going to talk, if we have time, over do the dates always match. And then finally, if we have time again, we'll talk about what to do when you're not sure, but you have to act. And that happens far more often than we like to believe or pretend. The varieties of radiometric dating, they're potassium-argon dating and argon-argon dating, uranium-lead dating and zircons, there's isochron datings, and so you'll notice that those are three of the topics we'll be talking about. There's uranium discordia-line dating, there's uranium disequilibrium dating, which again we'll talk briefly on. There's carbon-14 dating, yes. I'm not going to talk about that because I have another talk this afternoon that those of you who have the chance can go to. And that would just be too long. Now, radiometric dating has sometimes been likened to an hourglass, where you have stuff at the top, you have stuff at the bottom, and you look at it and you can tell how much time has gone by. It's probably more accurate to model it as a cylinder, or something with straight walls anyway, and has a hole in the bottom. And the higher the water is, the more pressure there is to push it out. And so what you wind up with is, and math phobics, sorry, just close your eyes, this will all go away. The radioactive materials decay according to an exponential curve. The amount of parent that you have at present is equal to the amount of parent you started out with times 2.718281828, it goes on, time to the lambda, the decay constant, times the time. Well, if you solve for that, you can get the time as the natural logarithm of the p that was present originally versus the p that you have now, divided by that time constant. That's the general principle of all radiometric dating. Now, it's pretty easy to figure out what P is, because you can measure it. How much parent isotope do you have now? The problem is figuring out what P was originally, the P0. And that gets complicated. Well, the P is equal to, P0 is equal to P plus the amount of daughter that has come from decay. Well, how much daughter has come from decay? That gets complicated. The daughter that's come from decay is equal to the daughter you measure now, minus the daughter that was there originally, minus the daughter that has somehow been added, plus the daughter that has somehow been lost. Okay? So as you can imagine, unless you can get some kind of a handle on what those numbers are, you're not going to do any accurate dating. Okay? If the parent has changed, forget about it. You can't use this math. If there's been parent added or lost, it depends on when it was, how long it was, and the math gets so complicated that people just say, forget it. If there's been parent moving in, we just won't even date. Okay. Now, radioactive materials decay at a constant rate. That's the theory. It's been dogma. Is it true? Well, not really, because we can measure slight differences in the decay. For those of you who are interested in some of the exceptions, they will be in the paper that will accompany this talk. But it's close enough for practical purposes. Well, was it always that way? Could it have been speeded up, for example, in the past? Yes. It would have taken a miracle. Of course, those of us who are in this room believe in miracles, so that's not a big surprise. Is there any evidence that this happened? Actually, yes, there is. There's a paper which is part of a book called the Rate Book, Radioisotopes in the Age of the Earth, and you can get it online if you want. Don't worry about that. That'll be in the paper that accompanies this talk as well. Okay, and they have a graph that really shows what they were doing. The blue data points are actually measured ones. They took various zircons and they heated them up to certain temperatures, and they show that the higher the temperature, the lower the temperature, the slower it goes, and it tails right into a creationist model perfectly. And you'll notice that this is a log scale, so it's way off. It's further off than it looks. The uniformitarian, the standard, things have always continued as they were from the beginning of creation model, is off by a factor of 10,000. 100,000, I'm sorry. Well, did Humphreys get any feedback, criticism, pushback? Well, one of them is nature can't do that. Well, maybe nature can't, but God can. But so that's only valid if you can rule out miracle. Well, what about the heat that would be produced? They don't have a good answer for that. Maybe that's a miracle. Maybe does God fool us that way? Well, he's only fooling us if we want to be fooled. That's one way of looking at it. And some of the heat will be useful in producing an ice age, which we heard about yesterday. The other criticism, which is probably a more valid one, is the evidence is not really reproducible. That was a one-off. Well, how do we know it's a one-off? Because nobody's tried it before. Nobody's tried it again. Well, actually, the people at the ICR and their colleagues are trying to see if they can find other sites where this has also happened. And then we're going to be stuck with, the radioactive decay rate, at least for uranium, has gone way up in the past. Okay? Fact of the matter is we don't really know. If it happened, I will say this, if it happened, it would totally invalidate whatever radiometric dating there was that was dependent on this, which wipes out uranium lead. And it might wipe out potassium, argon, and rubidium, strontium, and all those other ones too, maybe. So it's interesting, it's worth pursuing, but we don't really know. Okay, what about speeding up radioactive decay rates for some isotopes and not others? The interesting thing is this is a testable question. Nobody's tried testing it because the money and the resources, the laboratories are all controlled by people who believe that that couldn't possibly happen. And so they're not wasting their money on testing it. But we will see what happens. Maybe we can do something about that. Now, so I'd like to say that question could be tested, and I'd love to be one of the people to help get it tested. Okay, now, we're going to go to our first method of dating, potassium-argon dating and argon dating. How many of you have heard of that? Yeah, we have a few. Okay. Well, let me explain what's going on. The first thing to say is this is a very special dating method because in theory, you heat the rock up, you get rid of all the argon, and that means that you get rid of all the daughter element, so all the D that you measure is actually D star. It's actually produced by radioactivity. That's the theory. And I can quote you multiple textbooks. Guy and Schleicher, what is special about the potassium-argon method is that the daughter nuclide is a noble gas, which is normally not incorporated into minerals and is not bound in the mineral in which it is formed. Notice the weasel word normally. Dalrymple and Lamphere, potassium-argon dating. These are, by the way, professional books for professional people. So they are careful. A silicate melt will not usually retain the argon-40 that's produced, and thus the potassium-argon clock is not set until the mineral solidifies and cools sufficiently to allow the argon-40 to accumulate in the mineral lattice. That is to say, not usually. Notice the little weasel there. Okay. Dalrymple wrote a book to persuade creationists that the earth is really old and life on earth is really old. And it's called The Age of the Earth. And he says there, the potassium-argon method is the only decay scheme that can be used with little or no concern for the initial presence of the daughter isotope. This is because argon-40, notice, little or no concern. Boy, you know, we're going to shrink that weasel as small as we possibly can because we're talking to creationists and we don't want to give them any room to wiggle out of this. This is because argon-40 is an inert gas, does not combine chemically with any other element, and so escapes easily from the rocks when they're heated. Thus, when a rock is molten, the argon-40 formed by the decay of potassium-40 escapes from the liquid. Then when it cools, it freezes and it starts accumulating. That's nice. Okay, that should make it easy. Measure the argon-40, measure the potassium, 0.1167% of which is potassium-40. Then you plug them into the formula and you have the time at which the mineral was last heated above a certain temperature, which varies with the mineral. Okay, this is great. Well, it isn't that easy. First, there's the complication that not all potassium-40 decays to argon-40. Some of it decays to calcium-40. Well, we'll just have to throw another factor into our equation, okay? Next, when we measure argon in the rocks, there's plenty of argon-40 along with argon-38 and argon-36, just like in air. Wait a minute, I thought it drove all the argon off. Well, let's modify our theory. Actually, what happens when it cools, it absorbs argon from the air. And so you can measure the argon-36 or the argon-38, it's usually done with 36, so that we can kind of subtract out the argon-40. So our theory just got more complicated. The argon got driven off, but then was replaced by argon from the air. So now we subtract from our measurements argon-40 that is matched in a 295.5 to 1 ratio by argon-36. This is getting difficult. You should be asking, if the material loses all its argon, why does it then gain argon from the air? They don't usually address that. Okay, well, so here's the official formula. This part here comes from that argon that comes back from the air. This part here comes from the ratio of potassium to potassium-40. So all we have to do is measure the potassium instead of potassium-40. This part here comes from the fact that potassium isn't completely potassium. Oh, I'm sorry, the second one is not that. It's the branching ratio. Some of it goes to calcium, so we have to factor that out. And then this last thing down here comes from the decay constant itself. Okay. Now, but we're not done yet. Potassium argon H's are sometimes too old. And sometimes they're too young. How can that be? Well, something must have gone wrong. What could have gone wrong? Approach this from the point of view of a person who believes in long age and believes this should work. Okay? There are assumptions behind potassium-argon dating. Okay, one of them we already talked about, the decay constant and the branching ratio are constant. Okay, for right now we're going to accept that, even though we know that there's some evidence that might question it. The sample has lost all of its argon-40 at time t0. That's another assumption. Maybe it didn't. No argon has been lost since time t0. No argon has been gained since time t0, except that it came with argon-36 so that we can get rid of it. Okay? No potassium has been lost or gained since time t0, except for the decay of argon-40 of potassium-40 to either argon-40 or calcium-40. And we've already taken care of that branching ratio. Okay, the ratio of potassium-40 to total potassium is constant at present. And we can measure the potassium, the argon-40, and the argon-36 so that we can go back to that formula and plug it in. Okay? Now, if the sample is too old, something must have gone wrong. And they don't challenge 7. We can measure that stuff. They don't challenge 6. They don't challenge 5. They don't challenge 4 most of the time. They don't challenge 1. So the assumptions they're going to challenge are 2 or 3. So maybe this sample didn't lose all its argon, and that's why it dates too old. Or if the sample is too young, maybe it did lose its argon, so that assumption 3 is no longer valid. Okay. Without further controls, you can throw out any date you want. You don't like it? Well, it's too young because it didn't retain argon. Or it's too old because it kept some of the argon to begin with. So now you have something that can give you whatever date you like. If you don't like it, you just toss it and try again. Is this a problem? Well, yeah. I mean, actually, we're going to look at a paper that was picked out from me by a long age advocate who was trying to persuade me that I should really adopt long age. So it's their evidence. Okay? It's a famous paper. It's not online as far as I can tell. You might be able to get it. But if you did, you'd probably have to pay for it unless you could get it at interlibrary loan or something. They had 101 dates, and they were all lined up except for 2. And those 2, the younger one was dating 10.0 million years, and the older one was dating 9.9 million years. Only 100 million years, probably 100,000 years difference between the 2. That's not too bad. 99 out of 101 all lined up perfectly and only barely missing. Well, you dig into the paper and it's not quite that easy. For the evidence of their selectivity, let's see, they discussed on page 171 to 174 that all but one of the dates on potassium argon in Rusinga Island biotite was just tossed because they didn't match each other. I thought radiocarbon ages always matched. Well, the ones we show you always do. Then if you keep on noting that they continue to use biotite without any, wait a minute, we didn't trust it at Rusinga Island. Why are we trusting it here? So there's also the problem that, and I'm just going to read this and see if you can pick out the problem here. Unfortunately, many of the samples that passed field inspection, in other words, they looked good for suitability and were laboriously collected, later proved unsuitable for dating. Thus, of some 65 samples collected by M. Skinner, only 10 could be used. You are getting 15% of the data they collected in the paper. Well, no wonder you can get a nice lineup if you throw out all of the extraneous dates. That's a problem. And it's worse than that, because it turns out that you can get 4 different dates from the average rock. You can get the whole rock date, you can get the biotite date, you can get the perhaps sanidine date, you can get the pyroxene date, and they can all be different. So, you know, well, on this sample I like the biotite date, so let's keep them. Well, that's not the way you would do things in a regular scientific field like medicine or like physics or chemistry. That would never fly, right? Okay. The laboratories routinely ask what stratum your sample is from, so they know the answers that are acceptable. You know, I try to imagine I'm an emergency physician and I draw a potassium date and I send it off to the lab, potassium level, and I go, can you give me the potassium level? And they phone back and say, well, doctor, what potassium level were you expecting? That would not leave me with a lot of confidence in that lab. The newest version is argon-argon dating. Now, wait a minute. I thought potassium-argon was this beautiful thing that could give you these wonderful correlations. Why are we switching in midstream? Well, first of all, let me tell you about argon-argon dating. What they do is they don't want to measure the potassium directly. So what they do is they take the sample and they stick it in somewhere where they can have a lot of fast neutrons. That means a nuclear reactor. And they have to put it in a specific spot where there are a lot of neutrons going by. And the potassium-39 gets hit every once in a while by a neutron, and it pops a proton out, and you wind up with an argon-39. It's known as an NP reaction. Don't worry about it unless you're a physicist. So then what you do is you take the crystals, and you heat them with a laser, and you release the argon a little bit at a time. Okay? And you measure the argon-40, you measure the argon-39, and you measure the argon-36. And you take the 39 and you convert it to you convert it to potassium by calculation or by comparison with a known age control. Well, what if your known age control isn't really known age? Then we have a problem. A plateau age is found, whereas you keep going into the crystal, you keep getting the same date. That gives you a plateau. So you're creeping up and up and up, and finally you get over the top, and that plateau age is the real age of the crystal. Notice that the crystal we are now getting into the center of the crystal, the part that's hardest to get rid of argon from. So we're prejudicing our dates to get older dates. Now, this is all very complicated and expensive and difficult to calculate. Why in the world did they go for this? Well, if you have a lab procedure and you're changing it, there are 3 reasons why you change it. 1, the old method is more complicated. That clearly is not the case here. 2, the old method is more expensive. That clearly is also not the case here. 3, the old method is not reliable. It's not accurate enough. So we want to switch over to the new method, because the old argon-argon dating is a confession that potassium-argon dating is a failure. And the nice thing about argon-argon dating is that it has a lot more data points to choose from. So that means that if we're going to pick cherries, we have a lot more cherries to pick from. It's nice if you're trying to persuade yourself that long ages are really true, but if you're approaching this system and you're trying to decide, is this really reliable? Maybe not. It measures the insides of crystals, as I mentioned, which is the hardest place to get argon out of. Okay? Now, glass gets rid of argon much more easily, but you know what happens when they do glass dates? They're all too young. Frankly, I don't have confidence in potassium-argon dating as currently practiced, nor in argon-argon dating. You know, there are reasons why you might get gradations of potassium-argon dates, but they might not have to do with actual age. More research would be welcome, and we really need blinded research with all the results published. That's how you do it in a medical research program. If we have 100 patients that we're doing a drug test on, we can't just throw out 50 of them and not count them. That's considered poor practice if you really want to know the truth. Okay, well, what about uranium lead dating and zircons? Zircons have an extremely high melting point. They can oftentimes maintain their crystal structure in the middle of lava, hot lava. Uranium ions have just about the same size as zirconium ions, so they are oftentimes incorporated into the crystal structure. But lead ions are significantly larger, and they're not easily incorporated into the zircon. So when the zircon forms, it tends to include uranium and not much lead. So the theory has been kind of to dogmatize that and says it doesn't include lead. Uranium decays to lead through several steps. There are two major kinds of uranium, uranium-238 and uranium-235. And uranium-238 decays to lead-206, and uranium-235 decays to lead-207. Don't worry about exactly how that, the physicist will tell you it's true, and it is. This gives two different dates. Hey, if they line up, maybe we can trust them. And there's a thing called a Concordia line that tells you where they line them up. And you're going to see a Concordia line in just a minute. Okay. Sometimes these dates give an unbelievable history of zircon formation in the melt and raise the question of inherited age, and I'm going to show you an example of that. Inherited age has not had the investigation that it has had in potassium-argon dating, where we actually know that that happens sometimes. Lava flow that happened in 1910 dates 44 million years ago. There's a problem here. Okay. Uranium lead dating, there's an article by Maria Martinez Ardilla and Benjamin Clausen. Some of you may know that name. And a couple of people, I think Patterson is from USC. It was published in the Journal of South American Earth Science, and it published a whole bunch of data. So I'm going to take their data and look at it. And this, by the way, is on the internet. Okay, here is, you can see this kind of curved line, if I can get it right here, is the Concordia line. Notice it's not a straight line, okay? And in fact, if you look at most of these, they don't lie on the Concordia line, they lie on this line right here, more or less. That's called the Discordia line. And the theory is that something happened, something happened geologically right here, and something happened geologically right here. Well, that's almost the present. In fact, it could be the present if you drew that line just slightly different, so maybe that doesn't really count. Well, let's take a date. Let's take these ones. You'll notice they don't match. In fact, if you look at it, the uranium-235 to lead-207 date is about, what would you say, 21, 25, something like that. That would be 2.125 million years, pardon me. No, it's 25 million years ago, or 2 billion years ago, something like that. Okay, if you look at this date here, you notice that for uranium-238 lead-206, we've got, what would you say, about 1550 or something like that. Quite a bit of difference between those two dates. Okay, so keep that in mind. The uranium-238 lead-206 date is generally the younger of the two dates. That may become important if we get far enough on our lecture. Okay, so here's some real-time dates that they have, and they do match. Look at them. They are centered pretty close to that Concordia line, right? Yeah, I'd take that. Okay, here's some more. This one is 131 million years old. This one here is 104 million years old. This one here is about 98.3. This is just a photo from their article. Okay, let's graph some of the data they have. It's actually, I think, all of the data they have in the article. And you'll notice that most of this stuff is down around here. We'll enlarge this so you can see what it actually looks like. But you'll notice that they have some stuff here that's just off the chart, and they have some stuff here that's really off the chart. This one here is over 4.5 billion years old. That's older than the Earth by anybody's account. Okay? We enlarged that, so you can actually see what they look like. And you'll notice that we have those two arrows. This arrow is the really one that goes way out, probably past the top of this building. This one here probably goes up into here somewhere. Okay? But the rest of it, you can see, you have this kind of line that kind of sort of fits. Oh, you have a little bit of reversals and stuff. In case you're wondering, these red ones with the 2 pluses, for example, that is rubidium-strontium dating. There's another rubidium-strontium date, another one. And you'll notice that there's some quite wide 95% confidence limits. Okay, which is 2 standard deviations more or less. These ones here, this one is that's that 130 that you saw, that lined up perfectly well, but you'll notice that it's way above all these other ones. Why is it doing that? Why is it doing that? So then that one is uranium lead. The purple ones, because potassium produces a purple flame, so I thought that'd be appropriate, are potassium argon dates. And you notice, yeah, they kind of line up, sort of, if you use your imagination a little bit. But it's not a nice, smooth curve. And you'll notice that the uranium lead dates tend to be maybe a little bit higher than the potassium argon dates. I thought they all matched. Okay, that's the one that we talked about. Here's this date was just thrown out. They said, it's not a good date because it doesn't fit the curve. Well, maybe that one doesn't fit the curve either. Okay, so now rubidium-strontium dating is the most common form of dating using isochrons. There's a whole bunch of them. There's samarium-neodymium dating, lutetium-hafnium dating, rhenium-osmium dating. Some forms of uranium-lead dating are done that way, thorium-lead dating, potassium-calcium dating. And don't ask me why they do this, because I thought argon could get rid. They actually use potassium-argon dating sometimes with isochrons. Why are they doing all these dating? Because they don't get the results they want, so they torture the data until it finally gives up. In these cases, the daughter element is clearly not lost at the beginning. I mean, strontium doesn't vaporize. So it's got to stay in there. So how do you know how much strontium you have left? Okay, so what you do is you assume that the daughter product is mixed thoroughly, homogenized to within 1 part in 1,000 with a reference isotope at the time that we start the clock. Then a suite of minerals or rocks has more of the parent decay to the daughter in the standard way, but those minerals have more rubidium in some areas and less rubidium in others relative to the strontium, and so it piles up in an uneven way, so that some minerals have a higher ratio of the parent to the reference isotope than others, and eventually, if you wait long enough, they'll have a higher ratio of the daughter to reference than others. And you can graph that. Now, this is going to be a little math. Don't worry about it. Everybody agrees with it. A case of potassium, rubidium, strontium dating, the parent is going to be 87 rubidium, daughter is going to be 87 strontium, and the reference isotope by convention is 86 strontium. They could have chosen 88 strontium. They could have chosen 84 strontium. It doesn't matter. The math turns out to be the same except for the fudge factor numbers that you use. Okay, the derivation of the formula in the case of rubidium strontium dating looks like that. Now, I expect you all to memorize that. You got 5 seconds. But, you know, if you go through the math, it'll turn out that it will perfectly match. Okay. Now, you'll notice that the end product, which was 87 strontium over 86 strontium, and you can measure that, is equal to some number that you can calculate, 87 strontium over 86 strontium originally there, plus the 87 rubidium to 86 strontium ratio, times e to the lambda t minus 1. And of course, we can solve for t. That's good. There's no dispute over the formula. Note that the formula is y equals b plus mx. If you know your algebra a little bit, you'll recognize that as a formula for a straight line. And that means that we have a straight line. That means that if we do it right, we can measure the slope. And the slope, we can do a few little cranks, and we're going to get time out of it. Here's this is a teaching thing that I got. It's all over. You look it up on the internet on isochron lines, and you can see, whoops, let's see, there we go. You can see that, you know, there's a data point, there's a data point. If you have one with absolutely no rubidium, then it will be right there. If you have one with more rubidium, it tends to go up. Hey, nice straight line, right? Yeah, we could live with that. And according to Dalrymple, this is the age of the earth again, where he's trying to persuade creationists, he will say points that fall on an isochron can confidently be interpreted as indicating the last time of last isotopic homogenization, that is, formation or reformation of the rock. Thus, the isochron method is self-checking, providing not only the prospect of an age, but a statement on its validity. If you see one of those straight lines, you've got an age, period. So all you creationists, listen up. Okay. Now, the problem is there is another process that can give you a straight line. It's called a mixing line. Maybe I should explain that. Let's supposing that you have two magmas, and they kind of intertwine with each other, right? And one of the magmas mixes in a little bit, so some of it has more of the other one. And you get a sample from here, and you get a sample from here, and you get a sample from here, and you get a sample from the other magma that's kind of mixed with the first magma, and you get another sample out here, and maybe you get a sample, like that purple circle, that's half and half. You know what? They will all line up on that same straight line, and it will look for all the world like it's... Okay. Now, there's a derivation for that, and again, I'm only going to give you 30 seconds. You've got practice now. Okay. But everybody agrees that the math is correct, including the textbooks for people who believe in long ages. Okay. Now, in order to give positive ages, mixing lines have to have a higher rubidium-strontium ratio in the component that has the higher 87 strontium to 86 strontium ratio. Wait a minute. Positive 8, you mean you can get negative ages? Yes, you can. If I can get this thing. This can happen if 87 rubidium has decayed to 87 strontium, and it doesn't matter whether it's natural decay that's been there for a long time, or it has been accelerated decay will give you the same answer. So most of the time you're going to get an answer, and it's going to look kind of good. I don't know what's happening here. We're having trouble. Let's see. Okay. Now, how can we tell the difference between mixing lines and isochron lines? Well, it's not by the lines themselves, because they look exactly the same. It's credibility. Wait a minute. Credibility? Mixing hyperbole, and evidence as to whether strontium isotopes have indeed homogenized. Now, credibility, is it all subjective? Well, some lines date into the future. That can't possibly be right. You can't have a line that will melt in 370,000 years or 370 million years. Something is wrong here. Okay, and people reject those as mixing lines all the time. Now, some lines date so far in the past that nobody believes them. Well, what do I mean by that? Let me give you some examples. Here's a whole bunch of these. Less than 1.6 million year old lava. Okay, we might say 3,000-year-old lava or 5,000-year-old lava, but they would certainly agree with you that it's less than 1.6 million. Rubidium strontium age, 773 million years. That's not good at all. Wait a minute, I guess we're having some fun. Okay, and you can see there's a whole list of them. This was not collected by a creationist. This was collected by a person who believed in long aging. And nobody does any tests. They just say it has to be a mixing line because it couldn't possibly be a real-time, 5.3 million year old lava, rubidium strontium age, 1.5 billion years. Who are we kidding? By the way, that particular site was redone by the rate group, and sure enough, that's what they got. Okay. So what about dates that match long age expectations, but they don't match short age expectations? Well, you're just going to believe whatever you want to believe? Is it all subjective? I don't like that. You know? I think we should be looking for differing predictions using the different models. So, well, mixing hyperbole, there's a whole thing. I'm not going to bore you, but you can see what it looks like. Unfortunately, when apparent isochron lines match long age expectation, they don't test them. They just say they're mixing lines. Or they say, yeah, they aren't mixing lines because they gave us the right date. Then if they don't get the right date, they throw it out. Unfortunately, isochron lines, according to the literature, can produce mixing hyperbole. Why is that? Well, wait a minute. Maybe they were really mixing lines all along and they just liked them and they shouldn't have. In any case, those who believe that they're isochrons are not going to concede based on the data. Okay, so now they're the ones that are, kind of hanging on to the data, ignoring the evidence. Also, unfortunately, according to one source, mixing lines do not have to produce mixing hyperbola. And this is Faure. Therefore, a certain amount of scatter of data points above and below the mixing equation is commonly observed for suites of geologic samples that are in fact binary mixtures. Now I'm going to say that I think I'm getting really close, and so there's more, but I'm going to have to quit. So if you have further questions, we'll try to answer them maybe at the question and answer period. And at this point, we'll invite our second speaker, who used to be the first, to come up.